Today we will look at non-terminating decimals. The definition of that is a decimal with an infinite number of places to the right of the decimal point, or basically a decimal that never ends. One that's really famous and well known is pi. The number pi is approximately 3 and 1400ths, but it is a decimal that is never ending. Here's just a little graphic to show you that, but even though at the bottom of that block it shows that it ends with 9-3, it doesn't. Pi actually is a non-terminating decimal, and it goes on an infinite number of places. Other numbers you might have seen in college algebra are e, and there's going to be several that come up throughout these notes, but I just thought I would show pi here to kind of give you a little representation of that. A repeating decimal is non-terminating, but there's a block of digits that repeats. And then we talk about that block of digits that repeats, and we use the bar notation so that we don't have to keep writing that repetition. We can just write the part that repeats and put that bar notation over that. Note, a rational number may always be represented either as a terminating or as a repeating decimal. And so that's a really good thing to think about. A rational number may always be represented either as a terminating or repeating decimal, and we'll talk about that throughout these notes. First thing we're going to talk about is we're going to go from fraction form to decimal form. In 6th grade, this is a big deal. Even in the next lesson, we'll bring in percents, that you can go from a decimal to a fraction to a decimal, and then we bring in the percent. You might need to go from fraction to decimal percent, and vice versa. So number 1 says, find the decimal representation for each of the following. Use bar notation for repeating decimals. What is the period? Okay, so the first one we have is the fraction 5/8. Keep in mind that that line does mean to divide. And so to take this to decimal form, I'm going to take the 5 and divide it by the 8. And remember, there's a decimal assumed after the 5. And so I can bring that up because I can see 8 does not go into 5. And so once I put that decimal in, I can add a 0 and say, okay, well, how many times does 8 go into 50? Which will be 6 times to give us 48. Subtract, we get 2. We can drop a 0. 8 goes into 20 2 times with 16. We have 4, drop a 0. 5 times to get 40 exactly with no remainder. Now this decimal here actually terminates. It's a finite, not an infinite number of places to the right of the decimal. So there's no reason to write the bar notation or the period because it's a terminating decimal, which we talked about in a previous lesson. So my answer here is 625 thousandths. On part B, 1/11 means 1 divided by 11. We have decimal point to add the 0. 11 doesn't go into 10, so that's 0 times. So here, that would be 0 times. We have 10. Now we can drop another. 11 goes into 100 9 times to get 99. That's a remainder of 1. We can drop a 0. 11 doesn't go into 10, so it's 0 times. You can write 0, or you can go ahead and just add that 0. 11 into 100 9 times, and you can see that pattern's going to continue, and so it's going to be decimal point 090909. So we're going to have a non-terminating repeating decimal with a period here. So my answer is going to be equal to 09 repeating. The 0 and the 9 both repeat. Since that's 2 digits that repeat, that means that the period on this is 2. And that's part of the answer. How many digits repeat represents the period. Couple more like that. We have 1/15 that we're going to take, and I'm going to erase some of this just so I have some clear space to work. So 1/15 means to take 1 and divide it by 15. Same thing, I have to add that decimal point. 15 doesn't go into 10, so I'll say 0 times. That's where I can go ahead and add that 0, and I'll kind of skip over the step I did in the last problem. 15 now into 100 would be 6 times to get 90. That gives me a remainder of 10, and I can drop a 0. That'd be 6 times again to get 90. That's 10 again, drop a 0, 6 again to get 90. And so I see here that I'm repeating that 6. The 0 doesn't repeat, just the 6. So my answer is decimal point 06, but only a line above the 6 because the 6 is the only thing that repeats. Since there's only one digit that repeats, that means that on this one, the period is 1. And finally, our last one in this section, we have 17/45 that we want to change into a decimal. So we have 17 divided by 45, which doesn't work. So I add that 0. So we're going to take 45 into 170. That would go 3 times to give me 135. When I subtract, that would be 35, drop a 0. 45 into 350, that would be 7 times, giving me 315. That's going to be 35 again, add a 0. So it's going to be 7 times again, and that's going to keep repeating that 7. So for this answer, my answer is decimal point 37. But only with the line above the 7 because the 7 is the only thing that repeats. Once again, since I just have one digit that repeats, that means on this one, the period is 1. On number 2, we want to write the following decimals from least to greatest. We had a similar example in the last lesson, and the negatives can really throw people. So what you can do is if the negatives give you a hard time, drop the negatives, do the problem, and know that when you add the negatives back, it completely reverses the order of your answer. I'm going to go ahead and keep the negatives on mine and work with it that way, but I am going to line them up vertically, especially because I have some repeating decimals. So my first one is -4 and 34 hundredths. Then I have -4 and 34 hundredths repeating. So I'm just going to write that a few times to help me out. Then I have -4 and 34 with the 4 repeating. And then I have -4, 343 thousandths with the 43 repeating. And then finally -4, 434 with the 34 repeating. And you don't necessarily have to extend those out, but it really helps me when I'm looking at those numbers. Even up here, I'm going to go ahead and add zeros because it just helps me carry that place value out further. All right, so I want to go least to greatest. So when I look at how I've carried those place values out some, it makes it a lot easier for me to find the smallest number. Now because these are negative, I'm actually looking for the greatest value, but with that negative in front of it, it's going to be the smallest number. So when I look, the ones places is all 4s. If I go to the tenths, I see here this 4, that's the greatest in value, but with that negative, it makes it the smallest number. So the smallest number, it's actually this last one right here, is -4, decimal point 434 repeating. And since I've placed that, I'm going to mark it out because I want to know that I've already used it. The next one that I'm going to look for, all of those have 3s in the tenths place, and so I'm going to have to go one place past that. All of them have 4s in the hundredths place. So I'm going to have to go past that, and what I see now, once I go past that, here, that next digit, this is the only one that has a 4. The rest of those have a 3 or a 0. So this would have to be the next in line. And so the way that that's written is -4.34 with the 4 repeating, and that's the next one in order. All right, so I've already used this one as well. Now, when I compare the numbers that are remaining, when I look at it closely, I see that these two, once they're extended out, are the exact same number. Since they're the exact same number, it really doesn't matter which one I write next. So I'm going to write negative 4.34 3400ths repeating, and then I have negative 4 343 thousandths with the 43 repeating. And so I've used this and this. And then my greatest number here is negative 4 and 34 hundredths. So if you extend those numbers out, I believe it makes those problems much easier to look at. If the negatives are giving you a hard time, take them away, complete the problem. When you put them back, it will completely reverse the order of your answer. All right, on the second page, number 3, I want to write 3 rational numbers between 2/3 and 67 hundredths with the 7 repeating. So when I think about what 2/3 is, 2/3 is 0.6 repeating. So here is what 2/3 is. 0.67 with the 7 repeating, if I extend that out, I think it makes it a lot easier to look at. All I need to do is come up with 3 numbers. There's a ton of numbers actually, but 3 numbers between those 2 numbers. So if I think about, obviously it's going to have to start with decimal 0.6. The second number has to be larger, or it can be 668, that would work. If I have 668, that's between 2/3 and 67 with the 7's repeating. That one would definitely work. I could have 0.6. Instead of 77, I could have 73, or I could even have 670, 671, 672. It would just have to be smaller than 6777777 and bigger than 2/3. So there's a lot of answers to this problem. I did come up with 3 like the problem said, and it's just rational numbers. See, rational numbers, at the beginning of the semester we looked mainly at natural numbers and whole numbers, and then we added our integers, which added our negatives. When we added our rational numbers, we added in all of our decimals and all of our fractions, and so there's a lot of numbers between 2/3 and 67 hundredths with the 7 repeating. On number 4, it says use the fact that 1/10 repeating is 1/9 to mentally convert the following into fractions. This is really interesting. This is something that I did not learn until even after high school, as far as how to quickly convert this. Nobody showed me this. And so I know, of course, that a 1/10, if I just have 1/10, I know that that's 1/10. If I have that 1/10 repeating, that will always convert to 1/9. So when we look at this problem right here, when we have that 4/10 with the 4 repeating, what I want you to think about is 4/10 without the 4 repeating would just be 4/10. When it's repeating though, that becomes 4/9. And if you divide 4 by 9, you will get decimal point 4444444, etc. On part B, I want to show you the same thing. If it was 5 7/10 without the repetition, that would be 5 7/10. Because it's repeating, it's now 5 7/9. So that's very easy. Should be very easy for you to do. On the next one, we're going to do the same thing. It says use the fact that 1/10 repeating is 1/9 to mentally convert each of the following into decimals. So we're just going to go the other way. 2/9, as far as the decimal, when it's over that 9th, you know it's going to be the repeating decimal. If it was 2/10, it would be decimal 0.2, but since it's 2/9 now, it's that 0.2 repeating. If on part B it was 5/10, that would be 0.5. Since it's 5/9, that makes it 0.5 repeating. Okay, on number 6, it says write 45 hundredths repeating as a fraction in its simplest form. Now, same thing. If we just had 45 and it wasn't repeating, that would be 45 hundredths because that's to the hundredths place. Because we have 45 repeating, that's going to be 45 out of 99, just like the 10th was out of 9. And on this one, 45 over 99, that can actually be reduced. And so when we divide both of those by 9, we can reduce this to 5/11ths. All right, last problem of the day. It says write 9 hundredths repeating in fraction in simplest form. So once again, if it was 9 hundredths not repeating, this would be 9 out of 100. Because it's 9 hundredths repeating, it's 9 out of 99 because of that repetition, and that's easy to reduce to 1/11th.